So this is the first video on CC16 fuels, which is a paper 2 only topic. And we're going to start by looking at a definition of a fuel. So it's a substance that can be burned to release energy. If you burn anything, if you light anything on fire, it's going to release energy. Combustion reactions are all exothermic. They will release energy in the form of heat. But to be an effective fuel, you want to be able to release quite a lot of heat energy. So for example, if you had a piece of paper and you burned it, it burns so quickly that it doesn't release a lot of heat energy. On the other hand, if you were to burn something like coal, it burns for a lot longer, releases more heat energy, and is a more effective fuel. So alongside coal, we've also got natural gas and crude oil as the other typical fuels. These are all examples of fossil fuels, and they are all finite resources. That means that they will eventually run out. And the reason they run out is because we are using them much quicker than they form. Because they are fossil fuels, they have formed from the remains of microorganisms over millions and millions of years. So they're not something that we can just go out and make more of really quickly. And we're using them really, really quickly. Therefore, we say that they're non-renewable or they're finite. So in the future, we are going to need to find alternative sources of fuels. Of those three fossil fuels, the one we're going to pay the most attention to is crude oil. Crude oil, it is a liquid at room temperature. However, it's not a pure liquid. It is made up of lots of different hydrocarbons. Some of those hydrocarbons are in liquid form, but some of those hydrocarbons are actually in a gaseous form, dissolved into the liquid. Hydrocarbons are molecules that contain carbon and hydrogen only, and you need that word only in your definition. So they've got carbon, they've got hydrogen, they don't have anything else. Because crude oil is a mixture, before you can use it as a fuel, you have to separate out all of the different hydrocarbons. The hydrocarbons have different boiling points, so because you've got liquids with different boiling points, you can separate them using the technique fractional distillation. Again, this only works if the hydrocarbons have different boiling points. So before we look at fractional distillation in more detail, we're just going to have a look at some hydrocarbons first. So we said that they're molecules that contain carbon and hydrogen only. I've got 5 of them drawn here. The 5 that I've drawn here are all quite small. The largest one here at the top has got 5 carbons and it has got 12 hydrogens. But you can have much, much bigger hydrocarbons. You could have 100 carbons in a hydrocarbon. You could have 200 carbons. So they can be much, much bigger than what I have drawn here. I've also drawn all of my hydrocarbons in just the carbons are in a row. But that does not have to be the case. You can have your carbons organized into a ring structure. So I could have the carbons all joined up in a 6-membered ring. Because carbon is in group 4, it can form 4 bonds in total. At the moment, each carbon only has 2. So I'm going to add 2 hydrogens to each of my carbons to bring the total number of bonds for each carbon up to 4. So I've drawn a ring with 6 carbon atoms in it. You can have a 5-membered ring, a 4-membered ring, a 7-membered ring, an 8-membered ring. So they can exist in rings. They can also exist as branched structures. So here I've got 5 carbon atoms just drawn in a row, but I could draw 4 carbon atoms in a row and then have another carbon atom coming off here as a branch. And then I can fill in lots of hydrogens. So you'll notice that it's always carbon that is the backbone. And the reason is because carbon can form 4 bonds, hydrogen can only form 1. You're not going to have lots of hydrogens in a row because each hydrogen can only form 1 bond. So the way I've drawn these 2 hydrogens is incorrect. Because carbon forms 4 bonds, that's always going to be your backbone. It's going to be the backbone in your ring, the backbone in your chain, and then you just fill in the hydrogens around it. So they are hydrocarbons, and you have got hydrocarbons in crude oil. The hydrocarbons, I said, have different boiling points. So the smaller the hydrocarbon, the lower the boiling point. So if I just look here, I'm just going to rub this out for a second so I've got a bit more space. If I look at the hydrocarbons that I've got drawn here, the smaller the hydrocarbon, the lower the boiling point. So I have got a hydrocarbon over here that's just got 1 carbon and 4 hydrogens. So I'm just going to make this up, but I'm going to say that this has a boiling point of -50 degrees Celsius. That means it becomes a gas at minus 50 degrees Celsius. The one next to it has got 5 carbons and 12 hydrogen, so it's much bigger. So I'm going to say that it has a boiling point of 30 degrees Celsius. Again, I'm making these figures up, but the general idea is the bigger the hydrocarbon, the higher the boiling point. Okay, remember, if you want to melt or boil any substance, you need to overcome the forces that hold those molecules together. In each case, you have got weak intermolecular forces because they are intermolecular forces because they are all simple molecules. So you're always only overcoming weak intermolecular forces. The boiling points will all be relatively low, but as the molecules get bigger, those intermolecular forces do get stronger. Yes, they're still weak, but they do get stronger. Because they're getting stronger, you need more energy to overcome them. Okay, so the small hydrocarbons, very, very low boiling points, but as the hydrocarbons get bigger, the intermolecular forces get stronger and the boiling points increase. Because they all have different boiling points, as I said, you can separate them using fractional distillation. You can be asked to describe the process of fractional distillation for 6 marks. I've written the answer out for you here. Make sure you are able to reproduce this. In general, the points that you would absolutely need to include is that you're heating the crude oil. That causes the hydrocarbons to evaporate. Okay, the hydrocarbons with the lowest boiling point will evaporate first. Then those vapors will enter the fractionating column. The vapors will rise up through the column. When they rise, they will eventually cool down. And when they cool down, they will condense. Okay, remember, small molecules, low boiling points, large molecules, higher boiling points. And this is just what your fractionating column will look like. So there's lots of different hydrocarbons in your crude oil, but we separate them out into 6 main fractions. You need to know the names of the fractions, you need to know what they are used for, and you need to know their order. So at the very top of the fractionating column, you've got gases, stuff like natural gas. Underneath gasoline, another word for gasoline is just petrol. Gasoline is the more American term, so petrol is what we would typically say. And you've got kerosene, diesel, fuel oil, and bitumen. You need to know that order. The fractions that collect at the top, they are the smallest molecules, and as we said, if they're small, they're going to have a low boiling point. We can also describe these fractions at the top as being very volatile. Volatile, again, just means they are easy to convert to a gas. So they become a gas really easily. That makes sense. They've got low boiling points, so they're easy to convert to a gas. They flow easy. That means that they're easy to pour. And the word we use to describe when you're pouring something is viscosity or viscous. If a liquid is really thick and it's difficult to pour, we say it's viscous. If it's not thick, or if it's a gas, so if you've got a gas or a liquid that's nice and thin and it's easy to pour, we say that it's not viscous, or you say it has low viscosity. The other thing we can say is it ignites easy. It is easy to set it on fire. So if you think of natural gas, that's what we've got in our Bunsen burners in the science lab, or you might have in your cooking hobs at home. It ignites really easily. As you move down the fractionating column, our molecules are getting bigger and bigger and bigger. And right down at the bottom, at bitumen, you've got really, really large molecules. Because these molecules are large, they have got high boiling points, okay? Much harder to convert them into a gas. Because they've got high boiling points, not very volatile. So it's hard to convert them to gases. They're not volatile because they've got those high boiling points. Again, they do only have intermolecular forces, but the bigger they get, the stronger those intermolecular forces get. They do not flow easy. We can say that they are viscous. They are viscous. So if you compare something like ketchup to water, ketchup is thick, it is hard to pour, it is viscous. Water is free-flowing, easy to pour, it is not viscous. The larger hydrocarbons are harder to pour, they are viscous. They do not ignite easily. So bitumen is used for roads and roofs. It's like a tar. That's not going to ignite easy. It's not going to be easy to light that on fire. So it does not ignite easy. Remember that these are what we call fuels, okay? So the reason we're talking about how easy it is to set them on fire is that in order for them to release energy, you need to ignite them. So, you know, petrol, diesel, they fuel your car, but they only release the energy needed when they've been ignited. So in the engine of a car, you've got, you put your key in the ignition and it ignites the fuel in the engine, and then your petrol and diesel can release the energy to get your car to move. So it is important that you can ignite a fuel. If you don't ignite it, it doesn't release any energy. So yeah, you need to know fractional distillation. Know that the reason they can be separated is because they've got different boiling points. Be able to describe it in a 6-mark question. Know the order, know their uses, and know these general properties. I go through some worked examples there. And then if you scroll down a little bit further, there are some practice questions, which I will get you to have a go at now. So if we look at this one here, if we just look here at the hydrocarbons, so I've given you a definition. They contain carbon and hydrogen only. I want to know which of the above molecules are hydrocarbons. So just pause and have a look at that yourself and see which ones are hydrocarbons. Okay, so hopefully you have chosen the first one and the third one. Second one's got an oxygen. The fourth one's got a nitrogen. So even though they've got carbon and hydrogen, they've got something other than carbon and hydrogen, so they're not hydrocarbons. The type of bond formed between carbon and hydrogen, covalent, okay, 2 nonmetals. Carbon always forms 4 because it's in group 4. It wants to gain another 4 electrons, so it forms 4 bonds. If we scroll a little bit further, okay, so crude oil is a mixture of hydrocarbons, okay? The technique used to separate, fractional distillation. Why can crude oil be separated by fractional distillation? The hydrocarbons all have different boiling points. And don't say melting points, they have different boiling points. Why must crude oil be separated into different fractions? It's not useful when it's all mixed together. When you separate them out, then it can be used. All of the fractions have different uses. The state change, when you heat crude oil is a liquid. You heat a liquid, it becomes a gas. That state change is called evaporation or boiling. What heat state change occurs when the hot vapors rise and cool? So if you cool down a gas, it's going to become a liquid. What is that state change called? It's called condensation. Where is the column hottest? It's hot at the bottom and it's cold at the top. So you're heating it from the bottom. It's going to be hottest at the bottom. And the rest of these questions here, listing the main fractions. The fraction made of the molecules with the largest number of carbons. Okay, so we said that they're largest at the bottom. So you look at your fractionating column, you see that bitumen's at the bottom. So the fraction with the largest molecules is going to be bitumen. So you need to know the order so that you can answer all of these questions. So the largest number is the one at the very bottom, is bitumen. The smallest number of carbons, the one at the very top, that's going to be your gases. The fraction with the highest boiling point, that's going to be the one at the bottom, so bitumen. Lowest boiling point, one at the top, so gases. Which is a higher boiling point, petrol or fuel oil, so you would need to know the order. You've got petrol here, you've got fuel oil down here. The higher boiling point is going to be fuel oil because that's closer to the bottom. Remember that boiling point is getting lower and lower as you move up the column. So the highest boiling point will be fuel oil. So again, all of those questions can be answered if you just know the order of the fractions. Yeah, they're all pretty much the same. And then at the end, you've got your uses. Could be asked a 6-mark question on how you would separate it. What property do the hydrocarbons and gas have that make them suitable for domestic heating and cooking? They are very easy to ignite, okay? Gases are very easy to ignite. That means that they will release lots of energy when they are ignited. What property do the hydrocarbons in the bitumen fraction have that make them suitable for surfacing roads? They are a thick liquid, that makes them suitable for surfacing roads. This one, describe the relationship between the number of carbon atoms in a hydrocarbon molecule and the physical properties of the hydrocarbon. And the physical properties. So yeah, you're talking about the number of carbon atoms in the molecule and how that affects its properties. So if you have got lots of carbon atoms in the molecule, you will have a high boiling point and it will be viscous, difficult to pour, and it will be hard to ignite. If you have got a low number of carbon atoms in the hydrocarbon molecule, then it will have a low boiling point. It will not be viscous, it will be very easy to pour, and it will be very easy to ignite. So the number of carbon atoms affects those properties. Okay, so yeah, I said this is essentially lots of learning, nothing too difficult in this topic. But yeah, learn all about crude oil, about hydrocarbons, about fractional distillation, and about all of the different fractions, and you should be good. In the next video, I will go and have a look at the homologous series, alkanes and alkenes.